Let's talk about Lenz's law. Now, Lenz's law is one of the most difficult laws to explain because you have to go through this chain of logic, to get it. So let me just read Lenz's law. The induced current in a loop is in the direction that creates magnetic field that opposes the change in magnetic flux through the area enclosed by the loop. Okay, now if you can grasp all that, you're in good shape. But we have to go through it piece by piece. Okay, so let me zoom in a little bit. Let's see, okay, so read that. Okay, so the induced current in a loop is in the direction, wait a minute, what did I wrote? It's in the direction that creates, creates a magnetic field that opposes the change in magnetic flux through the area enclosed by the loop. Okay, now we're going to deal a lot with loops of a conducting loop. Now, I'm going to draw them as circles. They don't have to be circles. They could be squares, rectangles, ovals, amoebas. We don't really care, but circles are easy to draw. So, at least for me. So it says through the area enclosed by the loop. So here's what we've got. Here's a loop. And I'm trying to draw it in perspective here. Now, what happens, it says the area enclosed by the loop. See, we don't really care about the area so much outside the loop. We care about the area enclosed by the loop. Now, for right now, this is reality, okay? This is not, black magic. This is not Harry Potter stuff, okay? As much as I like that stuff. This really is true, but it's very, very strange. And it takes getting used to. So right now what I want you to do is accept this stuff. Just accept it, learn the rules, and then you'll be able to solve the problems. And then we can do some things that but I'm just telling you, at this point, if you try to make common sense out of this stuff, you're going to have a really hard time, because the more you study physics, the less common sense is going to help you. All right. The real world, the world of our everyday life, like throwing, if you're going to go outside and throw a baseball around, that's the world that our brain is designed to understand, okay, or adapted to understand, however you want to look at it. But this, why should the world make sense outside of the realm that our brain, is adapted to get? I'm telling you, it doesn't. And if you think E&M is weird, wait till you study quantum mechanics or relativity. Okay, it gets very, very weird. But if you like that sort of thing, if you like weirdness, and I kind of like weirdness, it's really quite wonderful. But it is hard. So anyway, here's the area enclosed by the loop, but it's the loop that we care about. Now let's suppose we have magnetic flux through the loop. So here's some magnetic flux, and I'm just going to draw a few representative lines of flux through this loop like this. And so here we have some magnetic field. Now we might have magnetic field outside the loop, but guess what?
Doesn't matter.
We don't care about it. Okay? What affects what happens in here is this. Now, what if this magnetic field here, B, changes with time? That is, it gets more intense. That is, I would have to draw more field lines in here, or it gets weaker, the field lines spread apart. Now, I can't draw in cartoons. I wish I could. But here's what I want you to think of. If I increase the intensity of the magnetic field with time, it's almost as if I have to bring in other arrows from outside and bring them in, don't I? To make this more crowded, I have to gather magnetic field lines that are outside here and squeeze them into this area. Well, that means that those magnetic fields are sweeping through this conductor. And so that magnetic field is going to apply a force to the freely moving charges in this conducting loop, and it's going to induce a current to flow. So when you change the magnetic field through this loop, you will induce a current to flow. That's what they mean by the induced current. It's the current that is forced to flow in this loop when you change the magnetic field enclosed by the loop. And now, the direction of the current is such that the magnetic field that it creates, that the current creates, will oppose the rate of change. Okay, and so, and now this is when we go back to Faraday's law, which says the induced voltage that creates that induced current is equal to negative d phi dt. The rate. This is the rate at which you change. What Lenz's law does is Lenz's law gives you that negative sign. It says, hey, it's opposed to the rate of change. Okay, the direction of the current, well, the voltage will be such to create a current that will oppose the rate of change. So let's say that I'm going to increase the magnetic field with time. So let's say it starts right here, but as time goes by, I'm going to increase the magnetic field. So as time goes by, maybe we'll do this really slow, but we're increasing the number of field lines up like that as time goes by. Well, that's going to, just a second, that's going to induce a current that's going to create a magnetic field that's going to point down. Because what am I doing? I'm changing the magnetic field up. I'm increasing its upness, right? The amount of flux that's up. So that will induce a current that will make a magnetic field inside here that's down. Now, what direction will that current be? Will it be this way, or will it be this way? Well, use the loop rule, grab it. You want it to go down, right? I want my thumb to point down. So the current, the induced current, will be circulating this way. Okay? What, you had a question?
Okay, I'm lost. I was talking to Jim before. What is the E for? What is?
Okay. This is the induced EMF. Now, it's a voltage. Okay? And the voltage is what drives the current in this loop. Okay, and you know what? Let me go back. That's a really great question. What is this? Now, I'm going to show you, I'm going to review the motional EMF that we talked about last time. Several of you were absent last time, so I'm just going to review that. I didn't get the video up on YouTube, I'm sorry. So here's what we did last time. We had a rectangular wire system like this, but we made these conducting rails, just like copper pipes or something, and then we connected them with a wire. Maybe there's a little resistor in here. And then we put immersed this in a uniform magnetic field. And then we put a bar across here that had a length of L from here to here. And then what we did was we forced this guy to move with the velocity. We physically grabbed it and pulled it to the right. Well, this is a conducting material. It's got charge in it, right? And remember the formula, and this is the basics of all electromagnetism, all boils down to this formula. What is the effect of a magnetic field on a moving charged particle? Well, I've got these free moving conductors inside this bar, and when I go V cross B, I use the right hand rule. If I force this thing to move to the right with the velocity to the right, V cross B, my thumb gets pointed up. Okay, well, so there is a force on these charges upwards. Now I take this equation and I divide it by the charge on each moving charged particle, is the charge of an electron, or our pretend positive electrons, thank you, Ben Franklin, is equal to V cross B. Okay, but what is the force on a charged particle divided by its charge? That's an electric field, so we're going to call that E equals V cross B. Now let's assume everything's perpendicular here, and I'm just going to drop the cross product. Now, if I multiply that, the force per unit charge by the length here, well, electric field times displacement is our definition for voltage. So there is a voltage from here to here, and that's what I'm going to call E. And E is equal to B. I'm going to multiply both sides of this equation by L. And E times L is a voltage, so BLV. And this is called motional EMF. But notice what was happening here. And again, this is a review of what I did last time, so I want to go a little faster. But what I'm doing here is I pull this thing to the right. I'm increasing the amount of magnetic flux contained by this here. If you go BLV, well, let me do a little trick here. Here I've got L. Well, I've got B, and then I have L. Now, what is V? Let's assume that V is a constant, and we'll just call it delta X over delta T for right now. And we'll make this the x-axis, right? Well, what is L times X? L times X. That's the area enclosed by this loop. Okay? And so when you go, so this is area. So what we have here is B times area over time. And I'm sorry, L times delta X. L times delta X is how much I change the area. So let me put a delta in front of that area. Delta area over delta X. Sorry about that. But what is And what is the magnetic field times an area? What is magnetic field times area? It's magnetic flux. So this is equal to the change in magnetic flux over a change in time. So, and I'm really sorry, I don't know a simple way of explaining this. You need to know this prerequisite knowledge. You need to go through the chain of logic to get it all. So it is hard. It is hard. Well, this right here. Now, what we're going to do with Faraday's law is that we stick a negative in front of this. And why do we do that? Because E is equal to negative. Now, Faraday's law, Faraday's law and Lenz's law. Lenz's law is almost like a corollary of Faraday's law. So this right here, look, if I take the limit as delta t approaches 0 and let delta t approach 0, this becomes a derivative. And, where did what come from? Okay, I'm going to talk about that here right now. The negative comes from this. When I pull this thing to the right, that forces moving charges to go up, which creates a circulating current going this way. But this current creates its own magnetic field. And the magnetic field in this case, if I take my right hand and circulate it in the direction of that, is upwards. Well, notice that as I move this to the right, what's my rate of change of magnetic flux? I'm increasing, as this bar slides to the right, I'm increasing the amount of magnetic flux contained by that rectangle, and this opposes it. So that's really Lenz's law there. And Lenz's law is going to, and the way we express that is, hey, the voltage is going to be such that it induces a current to flow through here that will oppose the rate of change of magnetic flux in that loop. Okay? Now, what you're going to have to do to grasp this is to think about it many, many times. You're going to have to just old-fashioned thinking and studying and reviewing it over and over again. Because that's, because it requires a logical chain of fairly abstract concepts in and of themselves. Okay? But I will say this, it's way easier than understanding tax law. Okay? Because at least if you dig down, this does actually make some sense. So that's so you really have to understand what these symbols are saying. Okay, and if you do that, it's not so bad. This is saying, look, this is for loops. Here is Lenz's law for loops. And Lenz's law says, look, if you've got a conducting loop, if you change the amount of magnetic flux contained by that loop, you're going to get a voltage in that wire. And we're going to talk about that voltage in a little bit. That voltage will force a current to flow, but that current creates its own magnetic field, and that magnetic field will oppose the rate of change of magnetic flux. In other words, it says, no, 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 I don't like change. Conducting loops don't like change. They're kind of conservative. They don't like change. They want to keep the flux the way it is. Okay? And so, now they don't win. They don't keep it the way it was. But the current tries to. All right? And so what I need you to do right now is to accept that, to understand that, and the why of it will come. The more you think about it, the more you study this, the why of it will come. But what I've come to observe of students over the years is that the students who have to understand the why at every stage, they have a really hard time here, because you have to accept so many things before you get to this that it, you just kind of throw your hands up and give up. So accept it for now. I promise you it's really true. And then, well, the why and the deeper understanding will come. Okay, the more you use it, the more you practice it. So that's Lenz's law. I'm now going to give you a couple of example problems to try to use Lenz's law to predict the direction of currents. So I'm going to do that, though, on a separate video.